Hello everybody, my name is Stefano Dalla Palma and I'm going to present our work accepted for publication at Transaction on Software Engineering. This study was conducted in the scope of the European project called Radon, which aims at providing a framework for serverless function as a service to help the European industry to create and managing applications based on serverless computing. One of the key pillars is the correctness of infrastructure code, and our work contributes to that pillar by providing practitioners with defect prediction models of failure-prone infrastructure as code scripts and investigating the role of process and infrastructure source code metrics for their detection. To this end, we present the Radon framework for infrastructure as code defect prediction, a fully integrated machine learning-based pipeline that allows for data collection, analysis, model building, and evaluation. We will describe the framework in detail later on in this presentation. However, the task in the European project is not the only reason we focus on infrastructure as code. As you may know, infrastructure as code helps DevOps engineers manage and provision infrastructures efficiently and repeatably using machine-readable files rather than usual manual configuration. At the same time, it reduces the time, effort, and specialized skills required to provision and scale infrastructure services while improving consistency by reducing ad hoc configuration changes and updates. Nevertheless, as the name suggests, infrastructure as code is still code, and therefore might be affected by problems that are similar to those presented in application code. Indeed, practitioners might change the infrastructure as code, and this can lead to the introduction of defects. Besides, practitioner lacks tools to quickly evolve and manage infrastructure as code, and current work is limited to academia. To give you more context, this slide shows a simple example of a buggy playbook, which is the name of referring to a configuration file in Ansible. As can be read from the issues and the highlighted code, a wrong condition at line 15 causes the code to fail. It is worth noting that this work focuses on Ansible, as it is the most common infrastructure as code language on GitHub and in industry. Therefore, here you can see examples of an Ansible playbook. A playbook consists of so-called plays, which map hosts to some well-defined roles represented by tasks. Each task is simply a call to an Ansible module. For example, ensuring the Apache and PostgreSQL are the latest version calling the YAM module. Modules execute the actual code to perform those tasks, and are used to describe or change the system state based on the input parameters. Let's now focus on the core of this work. In this slide, you can see an overview of the main four frameworks components, namely the GitHub repository collector, repository scorer, miner, and defect predictor. The GitHub repositories collector enables collecting active projects on GitHub based on user-defined selection criteria such as the number of stars, the primary language, minimum number of issues, and releases. It uses the GitHub's GraphQL APIs to collect the repositories metadata that are used to select the repositories that match the user criteria. Because Ansible is not tagged as a primary language on GitHub, we analyze the title, description, and folder structures of each repository to collect those based on Ansible. The repositories collected by the GitHub repositories collector are used by the repository scorer to pick relevant repositories. Indeed, a large portion of repositories on GitHub is not for software development, but are mainly used for experimentation, storage, and academic projects. Therefore, to mine only relevant projects, our framework verifies several constraints which are reported in this table. In particular, Criterion 1 allows the crawler to discard inactive projects, while Criterion 2 is needed because the target model are trained at the release level. These criteria are evaluated by the GitHub repositories collector. The remaining criteria are evaluated by the repository scorer and are considered as good indicators of software projects that leverage sound software engineering practices. Once the repository is deemed relevant for the analysis based on the computed metrics, its history is analyzed using the repository miner. The purpose is to collect failure-prone and neutral infrastructure as code scripts needed for the analysis, extract the source code and process metrics, and create the final dataset that have to be used as a ground truth for training a machine learning classifier. The resulting dataset of observation of failure-prone and neutral infrastructure as code scripts for the individual repositories are used by the defect predictor to build and evaluate the models. So let's see how we validate this framework through an empirical study on Ansible code. So the goal was to evaluate which classification techniques and feature the framework should rely on to achieve the highest detection accuracy, also to be used in practice. So the design of the study consists in 4 phases. The first one is the data collection, where we collected through the framework that we described earlier 104 Ansible-based projects and a total of approximately 5,000 defect fixing commits, 4,400 defect introducing commits, and more than 700,000 snapshots of failure-prone and neutral files. As classifier selection, we focus on 5 commonly used classifiers that also complement each other, like naive-Bayes and logistic regression, and resistant tree, random forest, and support vector machine. We evaluate the performance in terms of AUC, precision recall, and metric correlation coefficient, but we also reported the information for precision recall and F-score, although we refit the models to select the best one on the AUC precision recall. As a model selection strategies, we relied on a walk-forward validation, where we start training on the first release and test on the second one. Afterward, we test on the first 2 releases and test on the third one, then on the first 3 releases and test on the fourth one, and so on and so forth, until we test all the releases, until we train on all the releases minus 1 and test on the last release. The study consisted of 3 research questions, and the first one aimed at analyze to what extent the classifier selection impact the performance of machine learning models to predict the failure proneness of infrastructure as code scripts. The design of these research questions involved the 104 Ansible projects that we have collected, and we train 5 different classifiers, and then we use the Wilkinson rank test to analyze the differences between those classifiers, the performance of those classifiers, and reported the effect size using the Cohen's d. As a result, we have found out that random forest is the best performing classifier with an AUC PR of 0.9 and a metric correlation coefficient of 0.8. The comparison can be seen in the box plots and in the tables in the slides. We found out that random forest occurred as the having the best performance 98 times in total. So we can say that the models trained using random forest perform statistically better than those relying on the remaining classifiers, and the difference is statistically different with a large effect size. The second research questions aim at understanding how the prediction performance were affected by the choice of the metric set, that is, by the choice of process metrics, product metrics, or a combination thereof. So from the 104 Ansible projects, we trained them using a random forest, the best model from the previous research questions. But this time, we create 7 different sets of metrics. So we use the dataset using only the infrastructure as code oriented metrics, here abbreviated with ICO. Second dataset consisted of only those metrics plus delta metrics, which are the differences of those metrics between 2 successive releases. Another dataset consists of the infrastructure as code-oriented metrics plus the process metrics, and so on and so forth. We only analyze it using process metrics, we only train it using the delta metrics, or all the metrics. Again, here we computed the Wilkinson rank test to measure the differences. And finally, we compute the effect size using Cohen's d. As a result, we found out that the infrastructure as code-oriented metrics achieved the best results. As you can see from the box plots, they also outperforms the other metrics and also other combination of metrics. Therefore, the models which features our infrastructure as code-oriented metrics perform statistically better than those relying on the remaining metric sets. And even here, the difference is statistically significant with a large effect size. The final research questions aim at finding the best predictors. That is, what are the most selected predictors and their combination. So again, from the 104 Ansible projects, we performed a recursive feature elimination cross-validation using the random forest as an estimator because it was the best model in the first research questions. And as an outcome, we reported the most occurring selected features and their combinations. From the table, we can see that all the best predictors are infrastructure as code oriented metrics, confirming the findings of RQ2. And we also have a combination of them, like the number of tokens and the lines of code. The text entropy and the number of tokens, the lines of code and the text entropy, and so on and so forth. Hence, infrastructure as code-oriented metrics tend to maximize the prediction performance, and in particular, the number of tokens, text entropy, and the lines of code are the most occurring predictors. As a takeaway of this work, we can say that, at least for the Ansible-based projects, structural code metrics outperforms process metrics, although the latter is often more effective when predicting the failure proneness of source code instances in traditional defect prediction. The main contribution of this work is the Radon framework for infrastructure as code defect prediction. It consists of open source implementation that is available on GitHub, and 100 for defect prediction model for Ansible and their evaluation. The full paper is available online, as well as the replication package on GitHub.